Okay, so we're going to revisit this example problem. We worked this at the end of lecture 19, but the difference here this time is we are actually going to assume variable specific heats, right? So we are going to assume variable specific heats. We're still going to assume that it's reversible, okay? So if we write these down, you can write down, it's the same problem. We're just going to work it slightly different. You can write down as much or as little as you like here as you're following along. We know it's air. There's no heat transfer because it's adiabatic. We're given the initial pressure of 60 pounds per square inch absolute, an outlet pressure of 12 pounds per square inch absolute, excuse me, an initial temperature of 540 degrees Fahrenheit, and I've got an initial inlet speed of 200 feet per second. And also, they have told us to go ahead and assume that it's reversible. They're giving us that S Jones even. They want us to find the exit speed. Okay. Now, we've already worked this one previously. You can go back and look at lecture 19. We've set up the first law. We solved the first law. And we said, hey, this is the first law simplified. The only thing I don't know is V2, which I'm looking for, and I don't have any way to find H2. And then we did go ahead and solve that out. So the first law simplifies down to this, that V2 is equal to, right? So again, go back and watch lecture 19, example 2, if you want to know how I got to this conclusion. H2 is equal to the square root of 2, I'm sorry, V2, I apologize. V2 is equal to the square root of 2 times quantity H1 minus H2 plus V1 squared over 2. Okay. So that gets us to the exit velocity, but I need H2 in order to get there. How do I get H2? Well, I need to know T2 because it's air. It's an ideal gas. So if I know T2, then I've got H2, and I already know H1 and V1. Okay, so that's where we are with the first law. The second law, we said, well, it is, I'm going to stop sharing now. We said with the second law, most of it's still the same. If I use the mass, the entropy per mass version, delta S is equal to the integral of dq over t plus little s gem. It's adiabatic and reversible. And we're going to use Gibbs equation. We could say the integral from t1 to t2, c sub p, dt over t. I'm going to use this version because I know my pressures, because this one has minus r ln ratio of pressures. If I know my volumes, I might use the other form for an ideal gas. If I've got a closed system, I might use the other form because I probably know the volumes or the change in volume. If it's a rigid tank, then the natural log of 1 becomes 0 and the second term becomes 0. But anyway, for control volumes, you probably want to use this version because you probably know the inlet and exit pressure. It's not a guarantee. You can use either one for an ideal gas in either case. But at any rate, if we're going to use variable specific heat, instead of doing this integral or treating this C sub p as constant, we're going to say S2 minus S1, which is 0, then is going to equal, and instead of this integral, I'm going to say using variable specific heat analysis, this is S degree 2 minus S naught 2, or S degree, however you want to say it, S naught 2 minus S naught 1 minus R ln P2 over P1. And what I can do then is I can solve for S naught 2 because I can find S naught 1 because I know T1. T1 will give me S naught 1. It's a table property. Plus this R ln P2 over P1, which R is just a property we can go look up. So properties, I just need to know that it's air to tell me that the R value, and we looked this up on the last problem, the R value is 0.06855. If you don't know how to find table A1 to look up ideal gas properties, well, you need to get really good at that very quickly. Or you can go back and watch the previous video. I'll show you where it's at. The fact that I've got air and that I know T1 will give me H1 and S not 1. All right. You're welcome to go look those up. I suggest go look those up. I'm going to pause and come back with them. All right, you got them? Remember, 540 Fahrenheit is 1,000 Rankine. The English tables are in Rankines. 1,000 Rankine. So pull the values for 1,000 Rankine, not 540 Rankine, because you got 540 Fahrenheit, not 540 Rankine. So then we just need to calculate. I'll let you run your calculator. I'm assuming you're able to calculate S naught 2. Go ahead and pause here and record that. All right, you have an S naught 2 value. There's what I've got. Let me share screen. Let's go look and see where that brings us. Share screen. So I've got 0.64009, which puts me in between these two rows. Remember, I don't know if you remember from last time, we found our T2 to be about 636 Rankine, which would make sense that we are right on task we're basically agreeing with how we solved this problem last time. Okay, so I'm going to let you, what do we do now? Well, I need H2. Right, so based on that, the fact that it's air, ultimately I need H2 is what I'm after, because I need to go back in the first law equation. Right, I know I can find H1. I need H2, right? Given, well, yeah, I've already got H1. So I need H2 to go back into my first law equation. So you're going to have to interpolate between these H values. Your H is going to be somewhere around 150. You can't just say, well, it's 150, Steve. No, you go ahead and interpolate it. Get at least 3 to 4 significant figures, so our final answer is correct to 3 significant figures. So go ahead and pause here, interpolate, and get us an answer, and we'll go from there. All right, here's what I've got. That passes the initial sniff test, that is between the values at 620 and 640 Rankine. Is that the correct answer? I don't know. We'll have to compare our final answer with what we did last time to see how we do. So V2, right? V2 is going to be equal to the square root of 2 times, I'm going to use brackets. You might get by without them. Quantity. It's going to be H1 minus H2. Well, I've got H1 here. It's 240.98 minus 152.15. Remember, we've got a units issue because these are both BTUs per pound mass. And what I want is feet squared per second squared. So I'm going to have to employ this guy of 25037. And go look this up on the inside cover of your textbook. There's 25,037 feet squared per second squared for every BTU per pound mass. I still need to add to it the initial kinetic energy of 200 feet per second. That's going to get squared, divided by 2. The whole thing's going to get multiplied by 2, and the whole thing's going to get square rooted. Go ahead and get you an answer, and let's compare. All right, that's what I've got, which is essentially what we had last time, right? Within 3 significant figures, we're in agreement, doing it 2 different ways. Here we're doing it with a constant specific heat. Here we're using what's called variable specific heat. I used a variable specific heat to find delta S, or the change in the S naught values. Use that to track that back to enthalpy change. So now these are all table properties. Which one should you use? We get to the same place. If I go through and get a good C sub P average value through an iteration process, I get the same answer. So which one should I use? Well, it depends. Do you mind doing the iteration process? If you don't try to take fluid mechanics or heat transfer. You're not going to like those at all. Most people don't like those classes anyway, but it is what it is. You're going to have to get good at either programming a computer to do this for you, or you could program your calculator for my class. I don't mind that. But you're really going to have to learn this process to actually write computer code to do it. Or you might have to interpolate at least one value here. Imagine if T1 didn't fall in a row and I had to interpolate both of these values, right? So if I've got to do one, two, three interpolations, this looks pretty good, right? That's just me. I will mess up the algebra at least once on an interpolation if I've got to do it three times. I'm probably am not going to mess this up if I've got me a nice roadmap because I'm comfortable and used to doing it. So which one should you use? I mean, you see, we get to the same place. It's completely up to you which one you want to do. I promise you, after you work through the iteration process a few times, it's not as scary as it first looks. But I get it as a bit of a challenge. If you're very comfortable with your interpolation skills, there's nothing wrong with this approach. Either one's just fine. All right, I'm going to give my voice a rest because I've just done a whole bunch of videos. There is another part to this. We can look at what I call the K ratios, which does also technically require a guess and check. It's a lot easier. But it's kind of a third way to solve this type of a problem. We'll look at that next time, but I'm gonna have to give my voice a rest. I'm not gonna be able to do it tonight. So if you're watching these as they come in, you might have to go watch the older version of this and turn your volume up. But anyway, stay safe out there, guys. We'll see you next time.